You can.
All right. All right. Well, I'm Eric Lund. I work for HPE. Harold will be my in the room wingman. I appreciate that very much, Harold. And I'm going to talk to you about OpenShami on VTDS, which is the virtual test development system that I've been working on. Um, a little bit of upfront housekeeping. All of the software here is available in. Oh, hang on a minute. I need to move something down so I can see my notes. That's not what I want to do. Apologies for a second. I need to get this down here. There we go. So all the software and can config data that I describe here is public open source under the MIT license and currently being hosted in the Cray HPE GitHub organization. We're planning to move the OpenShami specific elements to the OpenShami organization as soon as we work out the logistics of getting there and have a little bit of time to do it. So that's that. The other thing is there's a lot of content in here, so we may have a short period of time for questions at the end. Please hit me either in the conference channel or privately anytime you like to ask a question or make a comment. I appreciate any feedback I get. And then finally, this isn't a demo. I think that was Alex mentioned that it might be a demo. It's not a demo. It's an overview of what I'm doing. So anyway, let's move on with the presentation if I can. There we go. So what does VTDS mean? It means two things, actually. It refers both to the virtual test development system itself, which is what the tool deploys. And mostly what I'm going to be talking about is VTDS as a tool for deploying virtual test development systems. And what that tool does is it automates creating and managing virtual test development systems and automates deploying an application like OpenShami onto a virtual test development system. So that raises the question, what is a
Eric, your audio just cut out. Are you still there, Eric?
system configs prior to production deployment? It's usually designed to be.
Eric?
Yes.
What's your audio for a bit there?
Oh, I'm sorry. Okay. I will try to stay pointed at my microphone wherever it is. So it's usually a sandbox system. It's usually a system that is designed to model the larger production system and is used for pre-production work. So a virtual test development system is that without dedicated hardware resources. So, and I should say, I'm hearing a lot of people talking about rolling their own virtualization solutions for this kind of thing, and that's kind of where I'm coming from on all of this. The motivation behind the VTDS tool is it comes from a couple of observations that I have made over a lot of years working on a lot of different products. For large application development, virtualization is a force multiplier. And I don't think that's any news to anybody in the room. It enables accurate and efficient CI/CD pipelines for continuous testing and integration. By modeling physical resources fairly accurately, a virtual platform can allow tests to run and produce accurate results, which is nice. And the virtual platform can be created on demand and destroyed when no longer needed, and therefore doesn't incur costs when it's not in use. So that gives you both your accuracy and your efficiency. But that's for testing. For developers, it actually goes a little bit further than that. It offers those two advantages for sure. But then it also allows a developer to test on virtual hardware that actually matches the hardware, while hardware is still either scarce or unavailable. So probably a lot of us have had the lovely opportunity of developing software for hardware that hasn't yet been built. That virtualization, if it can model what we think the hardware is going to look like, and then improve the model as the hardware begins to roll out, it gives us a chance as software developers to get in ahead of the hardware development schedules. And the other thing is that often when we're talking about HPC stuff, we're talking about big expensive systems. In-house resources are often scarce when you're trying to work toward a big expensive system. And so they tend to be shared, and then sharing leads to contention and other issues. And so virtualization allows any developer to have a little platform that looks kind of like the hardware that they can do their work on. And it allows the developer to do the work within the context of the larger application, which then gives them better confidence when they are getting ready to deliver their code, that they actually fit nicely into and they don't find out during integration testing that, oh wait, my thing doesn't actually work when it's deployed out into the real world. In addition to that, the other thing that developers often run into is the need to get back to a clean slate. And sometimes that's because you've been working on your particular feature, and you've been tweaking it and adjusting it on the running system because you want to get to work, and you've been trying to reflect that stuff back into your code. And then you get to a point where you say, okay, now I want to make sure that what I've done is actually truly reflected back in my code. Let me go back and wipe the system out and restart it. If you're sharing a system, that can be difficult. If you have a virtual system of some kind, then you can just do that, and it gets you back going again. Another reason why that's kind of useful is occasionally we run systems off the rails. And when you run a shared system off the rails, it screws everybody up, and also then you have to wind up reinstalling everything. When you run a virtual system off the rails, you blow it away and start it again, and you're good to go. So those are the things I'm preaching to I know I'm preaching to the choir with all this, but those are the things that's one of the things that motivated doing this. The other piece is that deploying and configuring virtual resources is often cumbersome. To get it right with a virtual system that's supposed to model a particular piece of hardware can be a challenge, and it can require a lot of tweaking as things evolve and so forth. And there's the initial development of whatever scripts or manual procedures or whatever it is that you're coming up with, your KubeVirt or whatever it is that you're going to do. That's one piece of it. Then there's maintaining it going forward. And if you're an individual who's trying to do this, that's all eating into the time that you have to do your work. And while yes, it is part of your work, it means that your productivity on your deliverables is lower because you're spending your time keeping that going. So to that end, we want an easy, repeatable way to deploy a virtual cluster and an application on top of it, to simplify and improve repeatability of automated testing, and to reduce a developer setup, teardown, and maintenance overhead associated with virtualization. So when we started to look at the goals of the VTDS architecture, we were responding to some lessons that we learned from several years of work on an internal tool that we had that was similar to VTDS. And we came up with the goals that we have here. The first thing I list here, it's not necessarily the first thing we ever ran into, but the first thing I'm listing here is we want to be able to migrate to a wide range of resource providers for the the virtual test development system that we wind up deploying. The tool should be able to deploy onto a wide range of or able to be adapted to deploy onto a wide range of providers. And one of the things that we discovered was it's really easy to make a virtualization that's tied to a particular resource provider. And then that makes it really difficult to move. And so we really want to have the part of the tool that deploys resources onto a particular resource provider be pluggable. We want to isolate the quirks and limitations of that particular provider within that pluggable code, and then present abstract concepts to the constructs to the rest of the tool that can then be manipulated via configuration. And we wanted to avoid implementing application-specific support within the resource provider. So if you have OpenShami at the top of all this thing running on it, you don't want to have stuff built down inside of the code that's deploying onto your resource provider that is aware of OpenShami. That makes things messy, and it makes it difficult to move to a new application, which is the next thing I was going to talk about. And it also makes it difficult to move to a new provider. So the next piece is we want to also support a wide range of applications. OpenShami is one thing that we would like to be able to run on this, but it's not the only thing we want to be able to run on this. And so we want to employ the notion of pluggability. We can plug in the logic for deploying a particular application to the VTDS tool, and then isolate the needs of a particular system that we're modeling for that application in the configuration of the tool, while isolating the needs of the application deployment mechanism in the VTDS code, the logic that actually deploys OpenShami or whatever other application. And then we can unplug that and plug in something else and go. And then the next step is provider limitations in particular can prevent accurate modeling of the target system. And we want to get the emulation as accurate as possible. So on GCP, for example, which is what we've been using as the foundation for our development here and what we used for the internal tool, virtual private cloud networks can't carry DHCP traffic. This is an example of one of these limitations, which makes perfect sense for Google. They don't want DHCP running around on their virtual private cloud networks because that interferes with what they want to do, and it's problematic. But if you're building a system management application like OpenShami, and you decide that you want to model it on top of nodes that are directly built into GCP compute instances, you're going to discover that you can't do the DHCP part, and the DHCP part is a pretty important part of a piece of system management software. That means you can't test the DHCP part. It means you can't really do development on the DHCP part, and so it leaves you with an inaccurate model that is difficult to make accurate. In addition, so we want to isolate those kinds of provider quirks into away and hide them from the application and the other parts of the VTDS tool. In addition to that, being accurate also comes down to making everything as configurable as possible all over the place. The trouble with making everything configurable as possible all over the place is it leads to really complicated configs, a lot of which, probably 99% of which aren't going to change from one deployment to another of the actual system that you're trying to model. And so we want to keep that out of the user's face. It's not that the user shouldn't have access to it. They should, because we want them to be able to tweak and and try out new configurations and see and do interesting experiments and so forth. But we don't want it to be something they have to deal with every single day. And so we wanted to make sure that the configuration of this thing allowed users. And when I talk about users, I should have mentioned this up front, but when I'm talking about users throughout this, I'm talking about users of the tool, not users of OpenShami or admins or any of that. If I'm talking about those, I will mention, I will clarify it when I say it. But we want to keep that overhead to a minimum for users. So diving a little bit into the important pieces of the VTDS tool, we have two areas. The first of which is the cluster that define key abstractions that exist within the tool, and are represented within the config and within the APIs within the tool and so forth. The first is the cluster. The cluster is kind of a misnomer because you might not be building a cluster. You might be building a system to model a single node or a bunch of clusters all connected together by a public network of some kind, or a cluster within a simulated data center, or some other kind of network topology. But the term the cluster gets across the notion of nodes, networks, connectivity, and topology. So that's what I'm using here. The cluster is a piece of the VTDS tool architecture, and it constructs the networks used to interconnect nodes in the system, and constructs the nodes used by the application. In the case of OpenShami, whether that be a management node that's actually running OpenShami, or a managed node, say a compute node that is being managed by OpenShami. And then it defines the network connectivity and topology within the system. And that's all driven off of the configuration of the particular cluster implementation you're using, and is driven by the code of the particular cluster implementation you're using. The pieces that it exposes are virtual nodes and virtual networks. So virtual nodes are what you would expect. They're the thing that actually either runs your application or is managed by your application. The virtual network is also what you would expect. It's a network connecting those nodes together. There can be many virtual networks within your cluster. It depends on what your topology calls for. And the interconnection of nodes within your cluster can be however you want it to be. The configuration bases this on node classes, which are essentially prepackaged templates for individual nodes, or for types of nodes that you would want to have. And so the idea is that every node in a particular node class may be connected to a given network, but nodes in another node class might not. I'm not going to get too deep into that, but that's the notion there. So you have your virtual nodes and your virtual networks in the cluster. The next piece is the provider. And the provider is the piece of VTDS tool architecture that manages the real resources provided by some resource provider. So I mentioned GCP. That's currently the provider that we have implemented. And basically that would be, in that case, you would be managing GCP compute instances and virtual private clouds and whatever other, and all the, on all the lower level stuff that's needed to make all of that stuff come together. And it ultimately provides a substrate to host virtual nodes, which we call a virtual blade, and a substrate to carry encapsulated virtual network traffic, which we call a blade interconnect, and then a place to keep secrets. So the provider is responsible for storing and protecting secrets. It's not responsible for populating them. The content of a secret comes from somewhere else in the VTDS application. It can come from any of the other parts of the application. But the idea there is that in the provider configuration, the secrets are named for the particular system you're trying to model, and then the provider will provide APIs to the rest of the application to allow the other parts of the application to store and retrieve secrets from the provider. So virtual blades are in the GCS, in the GCP instance are GCP instances. The blade interconnects are VPC networks, and the things that are interesting about these are a virtual blade is going to be constrained, and a blade interconnect is going to be constrained to whatever the underlying provider allows to be done on that. So we don't expect to be able to do complicated, very custom things with that. We use those fairly generically, and then we build our virtual nodes and virtual networks on top of that. One of the things that a virtual blade can do is to provide some of the computational work that would normally be done in a BMC. So, for example, you might host a Redfish or IPMI server on your virtual blade to allow you to manage the virtual nodes that live on that virtual blade. That's an example. You may have other things. There are services that can run on a virtual blade. So moving on to the picture then. So no real surprise here, but this is laid out as a layered stack with the provider at the bottom and the application at the top, and then the core driving everything, which sits as kind of a pseudo layer on top of everything. And we have a platform layer that I hadn't mentioned, but we have the provider and cluster in between there. Supporting all of that is a VTDS base library, and then configuring all of that are a bunch of configuration overlays that come in and overlay on top of provider layer implementation provided base configurations. Those base configurations provide the default config and also the reference config. So what's in the provider layer default configuration is what's configurable within that layer. Within that layer for that particular implementation. And so these looking at configuration, then we the core configuration on the top of all of this is kind of special. We've talked about the layer, the base configs. The core config comes in on top of the core's base config. And the core's base config deploys a system with entirely mock implementations of all of these layers and just allows the core to run through operations against them. I'm going to talk more about what the core does in a minute, but basically the core config typically lives in a file locally in typically a directory that is specific to the system that you want to deploy, not just the system type, but the actual system, the actual VTDS system that you're actually planning on deploying. That directory initially only contains the core configuration, and when you're in that directory, if you run VTDS deploy, which is a command, or VTDS remove, which is another command, it knows to look at the config file in that directory, and then it does everything it needs to do to build your VTDS from there. What's in the core configuration is the definition of where every layer implementation comes from. So these can come from either a Git repository or PyPy. So for example, our GCP provider implementation can be pulled either from the Git repository where we're developing it, or it can be pulled from as a published Python module in PyPy. All of these are Python modules, and then versioning. So for a Git repository, that would be a Git tag branch or SHA. For a PyPy, it would be a PyPy version, or a pip version, using a pip version string. And so that defines where all of these come from, so that the core can construct the actual running application when it's invoked. And then it also defines where the configuration overlays come from. And the sources of those are a Git repository, a file, an arbitrary URL, or information that's stored in the core config itself. And one of the things that we do in the core config itself is to overlay the name of the system, of the resources that we're using from our resource provider. So in the case of GCP, it would be the project name within GCP that is overlaid and then allowed to, and that way it's unique and also interpretable by the person who created the system. They can identify their particular system. And then so that it can take from any of those places, Git repository, file, URL, or the core config. And then versioning exists for Git repositories, similarly tag branch or SHA. And then finally, the core configuration defines the order in which all of these overlays are going to be applied. So the order matters. If you apply them in the wrong order, you'll get a different configuration. And so the ordering is also in there. So looking at the layers themselves, let's look first at the core. So when the core is invoked, you type like VTDS deploy, for example, to deploy your VTDS system. All that exists at that moment is the core itself. It then goes to its config, pulls in the config, creates for itself a virtual environment that only it is going to use, a Python virtual environment that only it's going to use, installs all of the layer implementations that are specified in that config into that virtual environment, and then restarts itself. And also it also can replace the base library, and then restarts itself using those as the plugins that it is going to run with. After that, it then sucks in the configuration overlays, merges them in the appropriate order, and feeds them down to the individual layer, the layer specific, or the layer pieces of that config. There'll be a chunk for the core, there'll be a chunk for the application, cluster, platform, and provider. It will take, for each of those layers, it will feed that piece of the config to that layer. The layer implementation does not get to see the config from any other layer. So there's no temptation to go look outside of itself. There are also layer APIs on each of these layers that allow access to the abstracted elements. And so that keeps it nice and clean and pluggable. So once the core is done doing that, it then drives whatever request the user made, VTDS deploy, for example, down into the layers in the stack, in the appropriate order for the operation. So for a deploy, that would be the provider first, because you got to get that out there and running, and then platform to get it set up and working the way, get the virtual blades set up and working the way you want them. Then the cluster to get your virtual nodes and virtual networks into place, and then the application to actually deploy your application out onto that cluster. For VTDS remove, the operations are driven in the opposite order, so that you can tear down appropriately and ultimately remove and release all of your resources. Let's see, is there anything else that I needed to say about here? No, that's about it. So that's what the VTDS tool does and looks like from an architectural perspective. Let's look at what OpenShami on VTDS is. So currently the OpenShami on VTDS implementation is using a GCP provider implementation. I want to develop more providers, and I have one in particular, or one flavor in particular in mind that I'll talk about a little bit later in this talk. But that was the first one we developed, and it's the one we've been using to do the development work on this. The OpenShami application layer that we've developed for VTDS deploys OpenShami in one of three, currently deploys OpenShami in one of three modes. The first one is based on the quick start recipe that probably many of you have seen. It runs OpenShami services in a Docker Compose cluster. It adds RAE emulation for Redfish for fake compute nodes, and Sushi Tools emulation of Redfish for interaction with LibVirt to be able to manage real compute nodes. That would be compute nodes that are implemented as virtual nodes within your OpenShami virtual network. And then it does Magellan discovery on either one of those networks of real or fake nodes, and runs that through ID mapping for reasons that I'm not going to talk too much about right now, and then passes that off to SMD. The second mode is a quadlet based deployment based on the 2025 OpenShami tutorial that Alex referred to earlier today. This runs OpenShami services in quadlets under System D. Installs and uses OpenShami the OSHAMI CLI, and does static discovery currently based on VTDS application layer generated node data. So we generate a nodes.yaml in the application layer logic, and then ship it out to the deployment, and then allow the deployment mechanism that runs on the nodes to use that to feed node data to SMD. It can support and boot real compute nodes. Now, these last two statements are actually not quite true yet, but they're going to be true very soon. I've done all this stuff manually, but I'm still finishing up the code to get it working automatically. So a little bit further out, but not too much. And we'll be seeing that. And then finally, we have a bare tutorial node mode. This is set up to allow people to deploy an OpenShami system or deploy a VTDS system and then run through the OpenShami tutorial, the 2025 OpenShami tutorial on it. And that allows for manual execution of the tutorial. All packages, users, groups, and so forth are installed and ready to use. And the system is configured to begin at the beginning of the tutorial phase 1 instructions when it's done deploying. Deploying one of these things takes about 20 to 25 minutes. Tearing it down is a little bit quicker. It takes about 7 or 8 minutes. And that's deploying onto GCP. Just a note on cost. We can run one OpenShami management node and a network of up to 4 managed compute nodes on a single GCP instance. And that instance, I say here required. I think this is required. I haven't tried scaling it down. Is an N1 standard 16 VM, which is 16 CPUs and 60 gigabytes of memory running on a virtual machine with nested virtualization. A note on that, I think the currently prescribed provider for running the tutorial is AWS, which requires you to use physical compute instances if they're going to have nested virtualization, which is required for the tutorial. Those come in at about $4.50 an hour. The GCP virtual machines that we're allowed to use come in at about 76 cents an hour in the United States, and up to $1.04 in other regions. It's the GCP prices their stuff regionally. So that's basically what's there with OpenShami on VTDS. There's a getting started guide, which you can find at this link. This is one of those things that will eventually be moving over to the OpenShami organization once I work out some details. We also have a bunch of canned configurations. So that core configuration that you need to do, there's a canned template for that. And there's basically two things in there you need to change. One of them is the pointer, the link that gets you to this GCP provider layer organization specific configuration. So you just need to change out this URL in there to get the one that was written for your organization. And then we'll get to and then the other thing you need to change in there is the base name of your system on GCP, and then you'll be able to run VTDS to deploy onto GCP. In addition to that, everybody who has an organization on GCP, which is what you'll need in order to be able to run any of this there, has organization-specific information. The things like an organization identifier, there's a billing number that, as far as I can tell, has no secrecy requirements around it, but it's up to you what you want to do with that. It's not a number that anybody can use for anything unless they're already able to log into your organization. And at that point, they're using it. And then there's a folder ID within your project or within your organization where VTDS projects will be created. And then a default base name, which is what would be overridden in any given user's core configuration. Those are the two things that need to be changed. All of the rest of these are there and define a usable VTDS that models a system that OpenShami would happily run on. And then if you want to, within the core configuration, you can modify that. You could add networks, you could change you could do anything you want within your core config for your particular system, or you can write your own overlays and add them to your organization to match what your organization is trying to build, but then have them canned and pulled in by everybody's core config so that you only have to manage them in one place. So that's the information on that. And if you need any of these, if you want to look at any of these, feel free to go out there. And then the code repositories and all of those configs will be moving over to the OpenShami organization. And then we have the code repositories for all the code that I've basically been talking about here, which and the OpenShami application code will also be moving over to the OpenShami organization. So some ongoing work. I want to add Magellan Discovery to the Quadlet deployment so that we can have both a dynamic discovery and a static discovery option there. So that will be then configurable within the application layers implementation config. Then I also want to be able to provide additional provider layer implementations, and particularly given the modest resource requirements of OpenShami, I'd like to create a provider layer implementation that allows VTDS to be deployed on one or more of the following. And that would be a beefy laptop or desktop machine, a lab server, or a network of arbitrary lab servers. And the idea there is to provide an entirely in-house option for using VTDS and obviate the need for setting up a cloud provider to do this. And I'm currently thinking about how that particular implementation would work, and hope to begin working on that soon. And then I'm open to other suggestions, and I'd like to hear them here if you've got them, or just contact me and we can talk, or whatever file issues, whatever you want to do from that perspective. So again, I'm Eric Lund. And the best way to get a hold of me is through the OpenShemmy workspace as @Eric Lund. You can also reach me at eric.lund@hpe.com. I'm a little slower at responding to emails. And with that, are there any questions?
Please, I see a couple hands going up, starting to go up, deciding not to go up. Wait, anyone besides Alex first? Okay, I'm walking over to Alex.
Thanks a lot. So as I'm watching this and trying to envision how we might take VTDS and incorporate it into OpenShami, what it doesn't look like the place where I would do development. It looks like it might be the place where I would do testing. Would you see VTDS being set up as part of a CI pipeline? Is
Sure.
VTDS something that you would see as an unautomated, like manual testing environment? Where would you see it?
So from a testing perspective, I could see it as something that you would invoke from within a CI/CD pipeline. The tool that we have in-house, we currently invoke out of our Jenkins pipeline that does CI/CD testing, but I think you could do it similarly out of a Git workflow. I haven't tried it, but I think you could. You would need the information necessary, the appropriate credentials in order to do it, but it would then spin up into a in the case of a GCP provider, it would spin up what you need there and then be able to run your pipeline against that. And from a testing perspective, I think it could be part of an automated pipeline just fine. I've certainly seen something similar done with the tool that was its predecessor.
Anyone else with a question or comment? Yes, far side of the room, but it's not Alex.
So Alex didn't run across the room to ask another question?
No, he did. You can hear me okay, right?
Yep.
I'm gonna say this looks really awesome, especially as we progress into a more CI/CD mindset as far as our systems designs go. I'm Adam Huff from Shell.
Okay.
Is there, and it looks like you've got it working in GCP. How cloud agnostic is this? Have you tried running in any other clouds?
I haven't tried running it in other clouds. That would basically involve writing a provider implementation for another cloud, which so it's cloud agnostic insofar as you can plug in the cloud that you want to be using. There is work involved in doing that, but once you've done that work, you've done it, and then you have it. It's been carefully designed from the ground up to isolate knowledge of the cloud from anything other than the implementation of the cloud. So, and I should note the layer configurations are specific to that layer implementation, so they can talk in terms of all of the details of that particular cloud provider or whatever provider you've got. But they produce the abstractions that I talked about. So for example, with Google, there's a bunch of little ins and outs that you have to be able to configure. Much of that is very Google specific within the GCP provider implementation. But the overall structure of the config presents a particular set of abstractions, and then how those are going to be made to work. So what I'm saying there is it's cloud agnostic insofar as you write code for your particular cloud version, and then what your core configuration says, oh, pull in the AWS cloud, pull in the Azure cloud, pull in pull in the OpenStack implementation, whatever it is that you want to have. but you have to have that implementation. And those haven't been written yet.
Hi, Eric. You hear me okay?
Yeah.
The Donnie Cooper from Total Energies. I have a few questions. So first is a comment: when industry looks to adopt things in the open source, we like to play around with things as well and try other people's software, but we also look for some longevity. So how is HP or Cray, are you consuming this, or do you see this rolling out into products or your customers, or is this something that you're doing internally as a sort of consumption software and project?
So this started out as a project to replace something that we were consuming internally, but we intentionally put it out into the broader world with the hope that it would be adopted for other purposes like OpenShami, and it will be maintained. As far as I'm aware, I don't get to set company direction, but as far as I'm aware, it will be maintained as a HPE open source offering. And so its longevity should be based on on that kind of community support of the community and from the community.
How many people in your team are working on it, and how many people are passionate to work on it?
So right now I'm the one that's working on it. However, there have been quite a few people in the past who have been working on it. Right at the moment, we have a lot of people focused on a lot of other stuff. And I am certainly the one who is the most passionate about it. Although my management is fairly passionate about it as well. And there are other people in the organization that really like what they've been doing with the predecessor and really want this tool available for their internal use. So yeah, so right now it's me, which limits my bandwidth in terms of getting stuff out. But
as Eric's management, we're passionate about it, and we'll work to open source it so that we can, and then provide training and stuff so that we can bring a broader community in to help maintain it as well. So it keeps going, not just that it's not a one-off thing. So. But
Yeah.
we're as Eric's management, I'm passionate about it.
Got some additional.
Anyone else with a comment or question? Thank you very much, Eric.
Okay, thank you guys for your attention to this and your time, and let's move it on.